new around here, my name's Dylan Dance. I'm doing a PhD in physics, looking for dark matter. So if you've got any ideas, let me know. Yes, I've checked my back pocket, checked under the bed. Grab a coffee, grab a chair, grab whatever you want. Let's get into it. We've come a long way from my bedroom. I can't tell you what that is, so don't even ask, all right? If I told you, I'd have to kill you. I really shouldn't threaten people on YouTube. If you're watching this, Ann, do me a favor, don't. Ann's the process engineer around here, and I didn't tell him I'm filming this, and he's not gonna like it. But you know what physicists are like, we don't listen to engineers, so I reckon we jump straight into this. But before we do, make sure you apply some time derivative of momentum onto that subscribe button. And I've just brought back the Daily Dance, but it's now called the Science Brew. So if you want a free science newsletter every day, bar weekends, you should sign up.
Hello from the future. So I've taken a few weeks to edit this video, and I realized I forgot to put in a CalVPN ad. So if you want to come support your boy, come check out the world's first consumer post-quantum VPN, which your boy built. And it basically just is a VPN which has post-quantum or quantum-resistant cryptography, which can protect you from powerful quantum computers, believe it or not. Come check out this video if you want to learn more, and has a 7-day free trial. Everything is fully functional, operational. Again, we had some problems for a while, but it's all back, and I'm about to add a bunch of new features, and there's some exciting things coming. So if you want to support this channel and me, you should definitely come check out CalVPN.
Alright, here we go. So he's dead. Well, I'm pretty sure he would have died. Distance. 1.8 meters. I mean, that should be displacement. Now they're showing displacement. I think they got that backwards. The first measurement was displacement because it decreased when he stepped backwards. Distance would have just kept increasing. If you're doing stuff like you do in classical mechanics. So hopefully the rest of the video is more on it. I'm sure it is. It's got how many flipping views, and when he touched it, it should have gone into, expanded into like a sum of positive and negative distances. That would have made more sense. This is where everyone's gonna put in the comments down under, it's just a stick figure, it's not real physics, mate. Like, chill out. You're right, I'll chill out. Let's, I will enjoy it. It's entertainment after all, so I'm not gonna explain too much of the math going forward, especially if it's classical mechanics, because I'm out if it's classical mechanics. And if there's stuff, that needs explaining, yeah, maybe. But I like what Dirac said, one of the most prominent physicists in history. He said, one should, what did he say? One should hold reference to the physical concepts. No, one should hold the physical concepts in one's head without reference to the mathematics. That's what he said. And that's what physics is all about. That's the difference between, the physics nerds and the math nerds. Math nerds just like puzzles and shit, and the physics people, they like to understand what's going on with the universe physically. The math is important, obviously. That's the tool for which we use, but math, after all, is just a bunch of tricky ways of adding numbers, as Richard Feynman said. So yeah, don't get too caught up in the math. It's beautiful and I love math, don't get me wrong, but physics is all about understanding what's going on physically. Think about it. Imagine thought experiments. And, I'm going to stop yapping. Nice. It's a very quick run. Friction. Oh, he's got a big head like me. Epic was MA, got us to the moon. Wow. Power. All nice parabolas there. Did it say 512 newtons? Could be a little off. Friction. Alright, so he's not moving on the spot. 250 newtons. 50 newtons. Where did the rope come from? Like, where did that just come from? Alright, I'm gonna make a prediction. I bet you later in the video there's some kind of like trickery going on with this. It's a star. It's physics, right? So they're probably gonna do like Interstellar or Back to the Future, you know, and he'll meet himself. It's because that's what physics stuff always does. Alright, now he's gonna lasso. Now you gotta give him like angular momentum. Oh, that's alright. So I said I wasn't gonna talk about too much more, but angular momentum is one of those really important things in physics to understand conceptually, because it comes up so much in quantum mechanics and stuff, and what it means in quantum mechanics is not clear initially, because you start learning about the intrinsic angular momentum of particles. You might have heard of this concept called spin, which is, you know, all things have it, okay, like mass, but it's not actually referring to, say, a particle spinning, even though you could calculate that it has angular momentum. So yeah, I'm gonna leave you dazed and confused with that one, because I think that's what physics is all about. That's what makes it so beautiful. You're not meant to understand it, you're meant to feel it, as Christopher Nolan said. No, so Einstein said the most beautiful one can experience is the mysterious. All right, so I want to open your mind and make, hopefully, people who are not in physics see that maybe you don't quite understand everything around you. And you might get the wrong idea from me. You might think I'm a know-it-all, as my mum used to tell me. But I actually feel like I don't know anything. Like Richard Feynman said, I have varying degrees of certainty about different things, but I'm absolutely certain about nothing. And you know, there's so many quotes that pop into my head when it comes to this stuff. You know, currently where we are in physics, it might look like we have so much worked out, but we pretty much know nothing. So I'm working on something called dark matter. I'm looking for it. And we know it makes up about 80% of the matter content of the universe. And that's not even including the matter and energy content. You know, dark energy is a lot more. Yes, I've looked in my back pocket, under my bed, can't find it. Let me know down under if you have any good ideas, but I think I'm going too many tangents deep with this one. But the beauty of physics is, you know, exploration. You get to sort of, I think that's what we are fundamentally, us physicists. We're explorer types, you know, and looking for, you go where the mystery is. That's where the most beauty is, and that's what makes it exciting. So please don't look at physics like it's a bunch of cold, hard facts, because it's not. Those facts will likely be overturned at some point. You know, general relativity, quantum mechanics, these great pillars of physics, we know they're kind of not quite right. And it could turn out to be that reality is just like an onion, and as you peel back the layers, there's just more and more, and it just gets more and more complicated, as Feynman said. But, or it could simplify down into like one beautiful equation, and then we'd know the mind of God, like Stephen Hawking said. And you might have heard of Sabine Hossenfelder. She's making waves in the science communication landscape with, you know, her whole thesis that beauty is leading physics astray. I'm not on that wavelength. I do think beauty is something deeply profound and magical. I'll leave this for this sort of talk for later in the video. I'm sure they're going to go into the theoretical realms. So whilst we're in the you know, classical, lots of experimental evidence for this stuff, that was quite a tangent. Back to angular momentum. All right, yeah, precession. That's very cool. Lots of physics lab demonstrators will demonstrate that one for you. I hope I inspired you with that little rant. That's the only reason I'm here. Right? I'm not here to educate you in these videos. I just want to inspire some kids or people to, you know, you can tackle this stuff. If I can do it, you can do it. A fool like me. All right. I'm a little confused because on this ice back there was no friction. He was running on the spot, and now it's moving. But anywho, all right. There's another mysterious prop falling from the sky. Kinetic energy. That's going to come into play in quantum mechanics as well as potential energy. Very important concepts. Don't ask me to define what energy is. So I love in these videos, I haven't made them for a while, but touching on the things we don't know about, because that's, like I was just explaining, that's where the beauty and the mystery is. And if I just go, oh, we know that, you're going to be like, well, this is kind of boring. And guess what? Energy. You know, it's like, it's still this loosely defined concept, I would argue, in physics. And you can't really have just like pure energy. It's not a thing. And maybe that is blowing your mind right now, because we talk about energy all the time in our world, from solar energy, maybe that's related to this, and to, you know, just energy moving through the grid. You'd think we'd understand it, wouldn't you? But it is actually a really esoteric sort of thing. Like, you know, maybe dark energy is sort of pure energy, and that's why we can't quite get a grasp on it. But anyway, got a little too much to do right now. I need to chill. This video is getting me too excited, I think. That looks fun. Whoever made this did a good job. I'm sure this video has gotten a lot of people, you know, sort of like getting them interested in physics. And that's what we're here for. Is that a rocket? What is this mischievous little bastard up to? Ah, I see. He's gonna slingshot himself or something. Or they should have made the rocket like land on the ground, you know, like SpaceX, and those the new Swiss students I was just reading about yesterday, I was telling you about. Alright. I think it would have been splattered when he hit that rocket, but okay. So he's like indestructible, I'm guessing. 42. What a reference, huh? I'm sure you all know that one. Someone let everyone know it down under. There's that mysterious, I don't know, it's gonna be like Carl Sagan, the ship of the imagination or something. Alright, did he just put a cowboy hat on? That's flipping cool. Oi, the Lorentz factor. Alright, well here's some interesting physics we could talk about. So, you probably don't know what the Lorentz factor is, and if you do, what are you doing with yourself? Get out there and touch some grass, right? It's basically just showing how like the measurements of like time, length, they're gonna change for an object that's moving, if you didn't know. You might have heard of time dilation, you know, space contraction or dilation. These things are real, and we've actually physically measured them. We have a lot of evidence for them. And if you want to know, this graph is representing the Lorentz factor plotted against the speed as a fraction of the speed of light. You can see c, it's very small there, that's the speed of light. Now, you can probably tell, I'm just joking. If you've done no physics, you're going to be like, what the hell is this? But this graph is showing, right, that the Lorentz factor is basically unity until you get the ratio V over C is about half the speed of light. And, you know, it's not surprising that we don't have any direct experience with this weird phenomenon because, you know, the Lorentz factor deviating from 1 requires an enormous amount of energy, and our spaceships cannot get anywhere near these kinds of speeds. So, you know, of course we see these effects in like particle accelerators at the LHC in you know, Switzerland, or the cosmic ray showers, but you know, we don't. A lot of when you explain this stuff to a lot of people, they're like, "Well, what the hell are you talking about? You know, time dilation. You know, well, it's real. We've measured it. We've done all kinds of wacky experiments to show this is a real phenomenon, and you know, we need to include it in our calculations for certain things. And one day, if we travel to the stars, yeah, this will come into play. All right, let's get on with it. This voyage. So the cowboy hat. I think there's a couple references going on here, but I don't know which one it is. So you might have seen Dr. Strangelove and How I Learned to Stop Worrying and Love the Bomb. That's a movie. Stanley Kubrick, one of his best actually. Definitely give it a watch. And Dr. Strangelove is kind of a play on von Neumann, who is maybe one of the smartest humans to ever live. What's his name? I can't think of his name. Described von Neumann as like a different species. So, yeah, he was notoriously very, very, very quick. At Los Alamos, they were doing problems on the board. Him and I think it was Fermi. And what's the other fella's name who, you know, come up with the idea of the hydrogen bomb? What? My brain's not working right now. But it was either Fermi or him. They would challenge each other to solve some sort of problem on the board each day, and apparently von Neumann would always win. And how's this? Von Neumann is basically maybe the greatest, and how do I put this? I probably wouldn't argue that, but he's certainly one of the most important humans to have ever lived for our modern world, because you might not know that all modern computers are based on the von Neumann architecture. All reprogrammable computers. So Alan Turing, you know, come up with the computer, obviously, but the von Neumann architecture was the first sort of, thing that pioneered reprogrammable computers. And so he's responsible for so much, obviously, but then also consider that he just pioneered game theory. He came up, it was his baby. And I'm pretty sure he did it whilst, you know, the war was raging. So just during World War II, he just happened to like poo out, you know, like game theory. And you might not know that game theory is responsible for pretty much how Google works, search, the mathematics that underpins it. So it's like, here's this one man who, you know, is responsible for all modern computers, basically, in some sense, and all of search, which is the most used thing on the computers. And then not only that, he also like showed that when Schrodinger came up with his version of quantum mechanics, and Heisenberg came up with matrix mechanics, and you know, they both won the Nobel Prize together, I think 1930 or 31 or something, with Dirac. Love Dirac. And these two versions of quantum mechanics, it was actually von Neumann who showed they were completely consistent and the same thing, equivalent, just represented in a different way. And he did this like very quickly, and I'm trying to remember the story. I think he was just got to this place, and it might not have even been what he was meant to be doing, but yeah, anyway, that was a huge tangent. So it was either between Dr. Strangelove, this cowboy hat, because at the end the general or whatever rides the nuclear warhead backwards, and he got on the rocket initially backwards down into the Ruskies, the Russians, Davai, and but the other reference is Cowboy Bebop, my second favorite anime, Space Cowboy, right? See you, Space Cowboy. You're gonna carry that weight. All right, so they're gonna demonstrate relativity here, and that, you know, light, or maybe not, speed of light. Yeah. All right. Wave, showing that wave is light is a wave. Sorry. For red. I think they just got that backwards. I'm sorry to do this to you guys. I know everyone loves this video, but I'm pretty sure they've gotten this wrong. So where it says greater than 400 nanometers, ultraviolet, I should say less than. And I think the same, yeah, the same there. It's the opposite. They've gotten the wrong. You know, remember the alligator, the eating greater than, smaller than. This is such a well-made video. It's awesome. Ah, gravitational assist. Gravity assist. Ah, that brings back some memories of meeting Buzz Aldrin. I got to meet Buzz Aldrin, believe it or not. The second man on the moon, but the first man to take a selfie in space, which is cool. I won tickets to meet him. It's a funny story, but I told you we were going to keep watching, but I won these. I'm not going to tell you the story. I've done it before. Another time, I took my granddad and took a selfie with him. It was awesome. They called him Mr. Rendezvous in the Apollo program because he actually had a PhD all about rendezvousing. So the team called him Mr. Rendezvous, and apparently at parties it was real fun because all he did was talk about rendezvous. And I think they actually used his what he came up with is in his thesis for the Apollo program and the rendezvousing with the different craft involved in getting to the moon. And he was talking about how we're going to get to Mars and how a lot of his ideas are used in doing that. So really brilliant guy. He's still kicking around, I'm pretty sure. It's over 10,000. I mean, it's actually way more than 10,000. Ignore me. Ignore me. Pretty sure that's a star. And whilst I put these titles as physicist, I am in the area of astroparticle physics, so I'm also an astrophysicist, my boys. Girls. Active in it. Oh, come on. Exactly what I would do. It's definitely going to work. The motion is definitely going to give it some thrust. I hope he does that falling into a black hole. They're definitely going to do that. Alright, they're showing the Lorentz factor again. Because we're approaching light speed, so time dilation, length contraction. Alright, there's a magnet. Sure. Are they going to start talking about quantum theory? Oh, he's done for. Oh, hey! Alright. I missed it. Keep going. Try not to talk too much. Very nice. Magnetic flux. Ooh, this soundtrack is very reminiscent of Carl Sagan's Cosmos. I've been jealous. There's a been jealous. Sure, okay. Very smart. Okay, well, this, if he goes through this and it turns off, that makes sense. That's how rail guns and stuff like that work. Okay, that shouldn't work. They're breaking the laws of physics with this one. So that doesn't work. Why? It's really simple actually. So see this rocket. Let me go back to where it showed. Look, so blue, I'm not even going to explain the physics of it. I'm just going to, look, we'll match the colors, yeah? So blue is on the left here. Now these magnets that he showed, I assumed they weren't permamagnets, but they stayed on. So look, so the blue is in front of the rocket, and you can see the red over here, and all you got to know is that opposites attract, right? No, that's not a real thing in physics, but so the red and the blue attract. Okay, so So that's good, that checks out. He would be moving towards this magnet, but as soon as he goes through it, it's blue on this side and red on that side. So he would be attracted back to the magnet. So you wouldn't be gaining acceleration from this. You probably actually wouldn't move. So the only way this works is if the magnet turns off as he goes through it, which is how what are they called, the coil gun things work. So you ready? Well, it's red on this side and it's blue here. That'd be attracting. So anyway, this time they've actually broken the laws of physics rather than just sort of not correctly done the notation. All right, it's a lot of. They should have done the nukes. So I'm sure you've all heard about or watched sci-fi where that you're in a spaceship and it gains speed by progressively exploding nuclear warheads behind the craft, so that it gets near light speed. Slowing down is another issue, but that actually works. This is a completely hypothetical, proper spaceship that could be created, and we could make one today and send someone up. So just need a volunteer. Star system. Asteroid field. There we are. Time dilation, yeah, because his Lorentz factor is not unity anymore. That's a quasar and a blazar actually, because it's pointed at us. I'm not going to explain this because I talk about these a lot in the other videos. Ultraviolet. So maybe I'll say one or two things. Very quick. The quasar. Some of the furthest things we can see in the universe, blazars particularly. And what are these? This sort of, you can see like light shooting out perpendicular. Well, you remember galaxies are like these sort of like flat disks. At the center of these galaxies, you have these supermassive black holes, and when they sort of turn on, we call that central region an AGN, an active galactic nuclei. And basically, what's going on? This supermassive black hole's sort of eating so much material. So there's so much matter swirling around, it heats up, and you've got all these magnetic field lines swirling around and breaking. And it results in these enormous jets that are shot off perpendicular to the black hole. And not just radiation, but also some matter in there. And it's accelerating protons to near light speed, like we can do at the LHC. And they're some of the furthest things we can see, because when they're pointed at us, we can see them on the other side of the universe, basically. That's all I have to say about that. Quasars, from quarks to quasars, huh? But they're going from quasars to quarks. From molecules to minds. Alright, there we go. So this is the supermassive black hole with an enormous accretion disk. Yeah, and there's the poles, event horizon, the photon ring. Yeah, that's singularity. So he's definitely going in. How do you like them apples? I'm sure you've all heard, like Neil deGrasse Tyson talking about how, the outside observer is going to see something very different happening to the Apple versus Apple experiences. That's exactly what I'd do. So I've always told people the way I want to die, the way I want to go out is by falling into a black hole. Maybe I shouldn't talk about the S word on YouTube, I'll get flagged, but that's how I want to be the first human to jump belly flop into a black hole. And I've definitely taken my cowboy hat and I'm going to swing it around. Hell yeah. And again, I'm not going to talk about what it's like to fall into a black hole because one, it's theoretical and we don't know what happens once you pass the event horizon. General relativity breaks down and it's a free-for-all. The laws of physics break down. We don't know. We have some ideas, but you'll hear Neil deGrasse Tyson talking about how for the person falling in, if you were to turn back, you'd see the universe out to the end of time, like time would progress rapidly and you would watch the end of the universe. Whereas if you were outside watching the apple would freeze on the horizon, it would never quite cross. Oh. Gravitational redshift, gravity. Alright, that's pretty cool. Gravitational pulses. That's the apple. What else? I think they're more referencing like Newton's apple, right? Gravity. It's fine. Where did the apple come from? It's about to get spaghettified. The gravitational gradient as it increases to infinity and beyond. Singularity. Inner horizon. So another cool thing that happens is if you were to fall into a black hole, as far as we can tell, is your time is actually sort of over there, because we live in space-time, and around a black hole there's so much gravity that it's not just bending the light, it's bending the fabric of the universe itself. Space-time is bending down. If you imagine a space-time to be a flat sheet, it bends. If you put like a star in it, it warps it, right? But if you put a singularity in there, it bends space-time to infinity. So there's like another whole universe in there. And so going back to what I was saying, like if you bend space-time, you're bending the time towards the singularity. So just like you can't escape next Tuesday from coming, right? You can't. It's gonna tick around unless you solve the laws of physics or something, or invent a time machine. Well, this guy's future is now the singularity, just like your future is Tuesday. It's kind of mind-warping to think about. So, deoxyribonucleic acid. So we're showing some. Okay, here we go. Electron orbital, proton quarks, antiquarks. Oh, that's cool. Neutrinos. We're going to get down to electrons and even photons, which are infinitesimal. They're like infinitely small, supposedly. Did I say world shape? Conform? Ooh. All right. Singularity. So a world line is just sort of it's something that's showing you. In four dimensions, which we say space-time has 4 dimensions. I think we've already talked about that. That the path an object will take in 4 dimensions. But it's also showing you here conformal field theory, 3 plus 1. So quantum field theory, right? The standard model of particle physics is a quantum field theory, which is also conformal. Maybe we shouldn't talk about that, because the more interesting one is below, which says anti-de Sitter space, 5-dimensional. So we don't live in anti-de Sitter space, we live in de Sitter space. I'm also not going to explain what that is, but I bring it up because de Sitter space can also be 5-dimensional. And it's showing you this thing below the world line, because if there is a 5th spatial dimension, well, it's outside our 4 dimensions. And you'd be able to like traverse time and stuff. Like that's how the end of Interstellar works, right? And you're kind of seeing the bulk, which is what they call it in theoretical physics. But again, we don't live in anti-de Sitter space. We know we live in de Sitter space, which can also have 5 dimensions. And just for a little bit extra, string theory, right, is basically dependent on it describes anti-de Sitter space. So that's one of the reasons why string theory can go in that rubbish bin over there, because we live in de Sitter space. However, I don't actually agree with putting string theory in the bin like Sabine Hossenfelder and everyone else, like Eric Weinstein and all those people. I think it's done a lot for physics actually, and it could still be completely correct, and we're just not quite at the experimental sort of ability to do the experiments necessary on like the Planck scale. maybe we never will be as either. So, but I say that as well because string theory, maybe there are ways to mess with it to make it apply to de Sitter space, and something like string theory for de Sitter, who knows? Because you got to remember, string theory is really just coupling quantum mechanics to general relativity. It's not even attempting to touch the standard model of particle physics, which is quantum field theory, to general relativity. Like, to do that, now that would be, you'd be knocking on heaven's door. I don't think that makes sense, but anyway. This guy's about to knock on heaven's door. But this might be my new favorite YouTube video. I don't mean mine, I mean this animation. So that is a Penrose diagram, which hell of a mind F. I'm not going to say that word. So what you're seeing here is basically, what do we use them for? They show you like the causal like structure and path of things, and it shows you how two things are kind of connected and how they, it's really tricky to even explain them. And you can see down there a white hole, which are completely theoretical, by the way. What are they trying to do here? So I guess they're just showing you these two objects. We use these things to, like, understand black holes and white holes, and the evolution of the universe. They're obviously two-dimensional diagrams, right? Showing four-dimensional universe. I should say as well, like, what they're really important for, which is actually a really profound thing to think about, is, let me go back to it. It is showing you an infinite universe in a finite diagram. That's pretty interesting, right? So you're looking, it's representing something infinite in a finite region, which is why it looks so trippy. And maybe you've heard of a white hole. It's referring, like, we could potentially have all come from a white hole, believe it or not. No, not that. I'm talking about the Big Bang. There's ideas and hypotheses that maybe what the Big Bang and inflation is just sort of where, coming out of a white hole and, we're in the inside of a black hole or something, right? It's very theoretical. There's no experimental evidence for white holes. All right, he's looking at himself. Here's the interstellar thing coming. Oh, there's quantum mechanics for you. So that's a probability wave. That's what it said. Okay. So we've got, see that weird trident looking. I said I wasn't going to explain any math, but I will here, because this is maybe one of. I said you should understand the physical concepts, right? And understand what's happening physically. But this math looks very hairy, so you might need some help. So this trident-looking thing, which is called psi, it is representing the wave function, which is not a real thing. It's a mathematical abstraction, although there is recent stuff to suggest maybe it is real, because it's a complex number, which means it has an imaginary and a real component. And so it's like, how could something with an imaginary component represent something in reality? It's interesting to think about, but then again, the complex plane is just sort of, perpendicular to the real plane. So yeah, I'm going to step off that tangent and back onto what it's showing. And what psi is representing is the wave function, which is, it sort of relates to a specific energy. It also represents, the quantum states. So there's lots to be said about this. And what the wave function represents is basically the probability that something, let's say a particle, could be in a given position or not in a certain position. And so you might be wondering why we use this. Well, from this mathematical abstraction, we can actually get a number which, is reflecting, is that even a word, of reality. And how you do that is you square the amplitude of the wave function, and that gives you a probability that, let's say, the electron is in a certain position around an atom in its orbital. There's actually a non-zero probability that it's everywhere though as well, which is, and you might have heard of superposition and entanglement. I'm sure they're going to go there. Maybe that's what they're demonstrating here. And anyway, we've talked about that too much in other videos. And maybe one last thing I'll talk about is how you can see the kinetic energy and the potential energy, because also what the wave function is representing is just like the energy for this of a system, right, or a particle. And you can calculate the wave function of anything. Like you could calculate the wave function of me or of the universe. Just my wave function would be very, very, very small. But as for when you get to very small scales, the wave function is the most sort of important part of defining particles. And you can see the kinetic and potential, because if you bring those two together, you have the total energy of, let's say, whatever it is you're describing. And you can see h bar there, which is probably the most interesting component. Maybe that's enough explaining this equation, but it's a beautiful equation, and I love thinking about it. Because you've got all these things around. It's just meant to be. Is that representing like virtual particles popping in and out of existence, which is when people say that, they don't really mean that. That's why they're called virtual. It's, more these quantum fields sort of bubbling, and constructive and destructive interference of this mathematical abstraction, the quantum field. And when we say particles, we just mean those sort of like this field, sort of like coalescing in area is sort of one way to imagine it. And so you shouldn't take it too seriously when physicists say particle. Anyway, it's just a useful model. You might have heard of like Hawking radiation, and that's sort of like the bubbling of particles popping in and out of existence on the border of the event horizon, and if one sort of on one side it falls in and one on the outside falls out, and that's how a black hole evaporates. But it's actually a little more complicated than that. That's just sort of a simplistic version explanation for it. It's actually, like I said, these quantum fields. But anyway, now this, the Calabi-Yau manifold, is something in string theory. It's like a thing to compactify dimensions, and it basically makes string theory work. It allows you to have more dimensions compactified in 4 dimensions, because we think we live in a 4-dimensional universe, and that's what this thing does. All right, it's very, very important to string theory, and it's important in math as well. This is very cool. I love this. What the hell is that? Ooh. Hyperbolic space. Einstein-Rosen bridge. Okay, wormhole. I'm sure you've all heard of a wormhole. You might not know that Einstein-Rosen bridge is the more sort of like technical term for it. And I bet you they're going to do something with entanglement, because ER equals EPR. Einstein-Rosen bridge equals Einstein-Podolsky-Rosen. What? Oh, right. Okay. Told you. One-dimensional open string. Closed string. Nice. Very, very smart, well put together video. I love it. There's a rod. Rocket. Oi! Alright, entanglement. So there you can see again the wave function or the energy And instead, they're using Dirac notation, bracket notation. You've got the bra and the ket. We're not going to talk about that. That's too much real physics. And entanglement, why? Because of what I said, ER equals EPR. They're equivalent. So just like if you entangle qubits in a quantum computer, you can get qubits over here that are entangled and qubits over there that are entangled, and you entangle everything, and it's like kind of like a wormhole. You can move in from quantum information from here to there via entanglement, and it's sort of like equivalence to putting something through a wormhole and from one region of space-time to another. Now, you might have seen that piece of news that Google made a wormhole in their quantum computer. It's not quite true, and it was completely overhyped and BS, because what they really did was, and what I just described, and why it's not quite a good, an accurate thing to say, is because it's in the quantum computer they were messing with at Google. It was in anti-de Sitter space. And remember, we live in de Sitter space. So again, I still haven't described the difference between those things. They basically lied. They didn't make a wormhole inside their quantum computer. It was like a virtual wormhole inside so yeah, I had problems with it. But still cool nonetheless, and pretty cool in this video. Triple cylinder sort. I missed that one. Walking radiator, there you go. Antiparticle, particle. But again, remember how I just explained to you? That's sort of, maybe I should cut the explanation from back there to put it there. It's not quite actually how they should represent it. It'd be very hard to visualize what we're talking about, right? Alright, you've got some mumbo jumbo. What's going on here? Alright. Also, just keep in mind, this is all theoretical beyond going into event horizon. The manifold, the string theory stuff that's now happening, except for entanglement and a couple other, they called it the probability waves. Yeah, those things is evidence for, but a lot of this is coupling sort of theoretical stuff, which there's no evidence for. So it's gonna confuse trick a lot of people. So it's just important to remember that this story won't make sense because it's coupling theoretical ideas with, solid, experimentally verified things. All right, so it's not like we know everything. We're very far from it. We don't really understand hot stuff, cold stuff, fast stuff, small stuff, big stuff, you name it. All right, so. Oops. Very much Interstellar. This is how Interstellar works, the end of it. And it was one of my early videos, so if you want to understand more of what's going on here, I'd go into sort of more detail in that video. That was beautiful. I loved that. I'm sure they'll make a sequel or something, right? So thanks for watching, guys. If you want to come check out the world's first consumer post-quantum VPN, it can protect you against those powerful Google quantum computers coming. The million qubit ones are going to be a problem if we ever make them, which we will. All right. Yeah, so come if you want to support me and help me keep making these videos, because I'm a poor uni student needing to pay off my student debt. Please come use my VPN. You get something out of it, and you support this channel. Or come, follow the Science Brew. I'm sending out a daily newsletter. It's a lot of fun, except for weekends. So please get behind me, subscribe. If you have any ideas for videos you want me to watch, just leave a comment. Let me know what you think of this video or anything. If you want to tell me how your day's going, leave a comment. And I'll see you guys in the next one. Hopefully I'll make one of these every week, and yeah, stay nerdy, guys.